Hello everyone, and thank you for joining us. Today we want to tell you about quantum orchestration for quantum error correction, and in particular focus on the importance of having a platform that allows to easily program quantum error correction from software while not compromising on the hardware performance that is so critical for quantum error correction. Before I dive into the technical details of quantum error correction, let me put an even broader context to this to motivate the discussion. Today in quantum computing, we're seeing two critical parallel efforts, which I call here the two races of quantum computing. The first race is the race towards quantum practicality, which focuses on demonstrating the value of quantum computing in the near term on NISQ processors. And this race is, of course, very important because only by showing real value in the relatively near future can we continue to push the field forward with more and more resources directed to it. Now, the second race is the race towards fault-tolerant quantum computers, which focuses on implementing quantum error correction successfully. And this race is very critical because only by doing quantum error correction and reaching fault tolerance will we be able to realize the full-blown potential of quantum computing in the long term. So at QM, we're actually pushing on both of these axes very, very strongly, but today we'll focus on the second axis right here, which is quantum error correction. And I think the word race is actually very appropriate because it's really important to maximize how fast we make progress towards fault-tolerant quantum computing. And here we should note the technical subtleties that are critical for quantum error correction because these technicalities make it developing quantum error correction, developing it fast, very, very challenging. So you see, while quantum error correction is clearly one of the most important focus areas of the field, it's also one of the most difficult areas. On one hand, it requires working at very low level with quantum machines and controlling quantum and classical operations with precise timing control on the nanosecond level. And on the other hand, the road is very long. So there is so much more learning and exploration to do in the next several years regarding how to best run quantum error correction that it's not so good to just build right away specific hardware that is maybe optimal for running a specific quantum error correction protocol, but it's not flexible enough. So new variations of the protocols are going to come every day, and we have to have a flexible system. So we really need to build tools that allow us to maximize how fast we do this, trying out new ideas and learning from them cycle. So we need to maximize how many times we do this cycle. And this is really about the compromise between hardware performance, extreme hardware performance, real-time hardware, and software programmability, software being able to develop very productively quantum error correction from software. And this is really what the quantum orchestration platform. So I'm going to talk about this, but before that, let's take a step back and talk a little bit about what quantum error correction is. So quantum error correction protects quantum information by storing it non-locally in the correlations between states of many qubits in a way that we can find local errors and correct them. Okay, so for example, we can encode a single logical qubits with 3 qubits as shown here. And you can see that if one qubit flips in this example, let's say the third qubit flips, the majority of the qubits are still in the correct state, and therefore we can correct the error. Now, importantly, you cannot just measure your qubit, what's called the data qubits that store the quantum information, because if we measure the data qubits, we collapse the state and we lose the quantum information. Instead, we need to be a bit more clever than this, and in this example, this could be done by measuring the parities between pairs of qubits. So we measure the parity between the first and second qubit and the parity between the second and third qubit. And as you can see here, before the error, these two parities were even and even, right? In both the 000 state and the 111 state, the parities are even. But after the error, when the third qubit flipped, the second parity, the parity between the second and third qubit, changed to odd. So these pairs of parities are called the syndrome. And by measuring the syndrome over and over, we can actually track the errors and we can correct for them. But this is very difficult, okay? This is very hard. To begin with, we must be below a certain error threshold on the physical qubits in order to run quantum error correction because we need to track the errors faster than they come. And on the other hand, we need extreme real-time control capabilities with real-time classical processing and ultra-low latency feedback that are needed for tracking errors, adapting syndrome measurements, correcting errors, producing magic states that are important to performing some gates on certain qubits or some gates on certain logical qubits, etc., etc. So quantum error correction is very hard. In fact, we at Quantum Machines, we know just how hard quantum error correction is because the first demonstration of quantum error correction was done by no other than our chief engineer and one of the founders of the company, Nissim Ofek. And here you can see just how complicated the control diagram was in this experiment, the first quantum error correction demonstration. And this is the control diagram for only error correction on a single logical qubit without performing gates on logical qubits and without scaling up to many logical qubits. And again, we want also the software programmability that I mentioned, the ability to develop different bits and pieces. Here, actually, there were tons of different tricks that were developed during the development of this experiment. And so we want the programmability. And here, QM comes into play. So at QM, we focus on the control stack of quantum computing. Our mission is to bring the best out of any quantum processor out there and allow achieving the fastest time to results in quantum development. Our control hardware stack includes our scalable and highly modular analog frontend. This is what drives the QPU, produces all the signals that drive the dynamics of the quantum processor. And then at the heart of our technology, we have our pulse processor. This is a new type of processor that is designed specifically for quantum control. And it's responsible for generating all the pulses and quantum measurements in the digital domain, and for sequencing and orchestrating the entire quantum program, as well as for the real-time classical compute resources that are, again, needed to run in real time. So this is the first key component for running quantum error correction. And the second key component is the interface to the pulse processor, which is QA, a first-of-its-kind programming language that allows programming quantum operations and classical operations in the same code so that they run together with precise timing control and they can affect each other. And this is what really makes quantum error correction so easy and flexible. Okay? A bit less related to quantum error correction, we've integrated many other cool things into the hardware, like coprocessor, stream processing capabilities, high bandwidth networking, storage and caching of programs, and more. And this is to integrate to heavier classical processing resources and to start running more complicated workflows of calibrations and applications, etc. Okay, very quickly in our software layer, we have two ingredients. We have our integration with higher layers of the stack. For example, our integration with OpenQASM3 that we are releasing these days, and Entropy, our calibration and QPU abstraction platform that allows automating complicated calibration flows. Okay, but for quantum error correction, the most important components are the pulse processor and QA. It's exactly this combination that allows programming quantum error correction as intuitively as basically writing pseudocode while getting the real-time control or the real-time hardware performance, which is in fact the best in the field. So just before we look at some examples, and actually Leo here in the next talk is going to dive deeper into specific examples, I just wanted to give you a very brief overview on some of the main components of QA, which allows such programming. So first, we can play pulses to elements in the quantum processor as well as perform measurement. These are the quantum operations. Second, we can define completely general classical variables like these A and B here and perform completely general classical processing with these variables. And this is really what makes QA unique because it interleaves classical and quantum processing. And then we can use these classical variables in the sequence. So for example, we can use them as the parameters of pulses. Here, for example, we modify the pulse amplitude or the pulse duration according to these classical variables. And another very critical component is that these classical variables can also be fed by measurements of the quantum system. So here we measure the qubit or the resonator into this variable I, and then we can keep processing this variable I. And then we can do control flow. So we can say if my qubit is in the excited state, I want to play something. If or while I'm measuring some error syndrome, I want to do something, etc. And finally, we have full timing control with sync and async multithreading. Okay, just to give you a concrete example, and again, Leo is going to give you in the next talk deeper examples. I just wanted to flash out there this really neat example of the easy stop algorithm from AWS concatenated CAD code paper from December 2020. Here on the right, you see the pseudocode of the stop algorithm, which includes complicated things like repetitive success loops and a lot of control flow based on real-time processing. And on the left here, this is the QA code, which in fact resembles a pseudocode really nicely. So I won't go into the details here, but I just wanted to show you that really when you write these complicated quantum error correction protocols in QA, it's almost as if you're writing pseudocode while you're getting the real-time hardware performance. Okay, so next, Lior Ela, who's leading our research and strategy, is going to talk in much more detail about how this is used to implement some of the major quantum error correction protocols discussed in recent years, such as adaptive parity tracking in the surface code, and such as adaptive error syndrome measurements, Honeywell, from their publication earlier this year, or last year. Before I hand it to Lior, I would welcome you to join us in our daily quantum orchestration platform workshops. We have on Tuesday, Wednesday, and Thursday. Here are the times and the locations. And also, please join us in our booth 609. We have a huge team of QMers who would love to chat. So with that, thank you very much.